Okay, here we are in quiz 10, and doing units conversion, you can never practice it too much. So remember the format. You're going to multiply this by 1. Understand that if you multiply something by 1, it doesn't change. And what's the 1 going to be? It's going to be a 1 that has rotations in the denominator and radians in the numerator, so that the rotations cancel. And so that conversion factor, that's 1 rotation equals 2 pi radians. So this is how you show it with the cancellation. And that's how you get the 8 pi radians. And you can leave it that way, or you can convert it to 25.1, 3 significant figures, radians. Okay, let's go to part B. Okay, so as instructed, I take the equation from the equation sheet. This is equation, oh, I don't have it in front of me, but I think it's equation 1.3 or 1.2. Anyway, average angular velocity equals change in the angular displacement over the change in time. The total change, right? So it just gives us an average. And so I write the equation. Now I substitute the numbers in with the units. Notice I have units with these numbers. And notice I didn't use the 25.1 because we want to avoid a rounding error. So I took 5 digits. You know, it actually goes on further, but with 5 digits, I don't have to worry about a rounding error. So 25.133, and then I divide it by the 5 seconds, and I get this. And of course, the final answer, and the reason I want this is because if I'm going to use this in a calculation, I'm going to use the unrounded number. But when I report, and I shouldn't have circled that because you're only supposed to circle the real answer, and the real answer that you're going to report is 5.03 because the 265 rounds to 3, and that's radians per second. Let me just say quickly, the radian, this can be written as 5.03 1 over seconds because radian isn't a true unit, because it's the ratio of 2 lengths which cancel. So radian isn't a true unit, and you'll see sometimes it mysteriously disappears. Part C is a little tricky. The equation, which is that omega average equals omega final plus omega initial over 2, right? The average is the sum of 2 numbers divided by 2. But that equation doesn't stand alone on the equation sheet. It's buried in equation, I think it is group 2, number 2. Anyway, if we write that omega average is this, and we look at this, we see that omega final over plus omega initial over 2 is omega average. So this is the equation we want to solve this problem. So we multiply both sides by 2. That leaves omega final plus omega initial, but omega initial in this case is 0. So doing the algebra, we get that omega final equals 2 times omega initial. So this is the kind of, when you don't have the equation right off the equation sheet, this is what I'm talking about when I say I want you to show me the work, show me the algebra. Okay, so now we have the equation that's going to solve the problem, that the final velocity is 2 times the average. So I put the numbers in, and notice I don't use the rounded number. And I put the units in with the number, and I write down the unrounded number, and then I write it down as I'm going to report it with the units. It rounds to 10.1. So that's our omega final. Okay, so since we just got omega final, we might as well use this equation. I think it's group 1, number 4, or it's the rearrangement of group 2, number 1. Acceleration is simply the change in velocity over the change in time. And yes, that's average, but since it's constant, we can use it. And so the change in omega is omega final minus omega initial, and this is 0. So we simply have omega final over the time, and omega final, we just got it, we divide it by the time. Remember, the time is the time from omega final to omega initial. So that's the total time. And it gives us this for an answer, radians per second, or 1 over second squared, or rounded 2.01, whoops, I made a mistake, radians per second squared. Now, you could use equation group 2, number 3, that delta theta equals omega initial t plus 1/2 alpha t squared. We often use that, and it would work here. But usually we use this when we don't know omega final, right? Since omega initial is 0, that cancels, and when you do the algebra, you get alpha equals 2 times the angular displacement over the time, the total time squared. So that's another way of doing it. Okay, following the format, we want the tangential velocity. So that's equal to omega r. That's group 3 equation, group 3 number 2, I think. And so we get that for the flag, so it's the radius where the flag is. So from the center to where the flag is, that's the radius of the disk. So we have omega final from previously, we have the radius of the disk, I left it in centimeters, and so my answer is in centimeters per second. But if I move the decimal point 2 places, I can change the centimeters to meters. And when I round to 3 digits, I get 1.01 meters per second. I can also leave it as 101 centimeters per second. If I leave it this way, it's not quite right because it has too many significant figures. So that's our V tangential final. Okay, part F. So the flag goes through the photo gate. It's such a short time that we ignore the fact that there's a little bit of acceleration going on, and we treat it as a constant velocity. So just the velocity at the end is the velocity it goes through the photo gate at, and velocity is just the distance over the time. Or when we're talking about a tangential velocity, we talk about the distance as an arc length, right? So anyway, the distance, whether we call it delta S or delta X, is the width of the flag, the 2.5 centimeters. Oh, anyway, that's the equation. Notice I solved it for time. Time equals the displacement. Oh, well, I changed the S to delta S to S. So the time is the distance over the velocity. So in centimeters, there's the distance, and there's the velocity. And notice I canceled the centimeters. I put the units and canceled them. That's what I'm looking for. And then when we do the numbers, that's the result we get. And notice that the units, centimeters, cancel, and that leaves me with 1 over seconds, which is seconds. And that's the number. And it should be, right? The photo gate times are always just a few thousandths of a second. And so that makes sense that it would be a very short time. So finally, when you're talking about tangential acceleration, rotational or angular acceleration, and centripetal acceleration, the first thing you should always do in physics is write down the equations. So that any acceleration is the change in velocity over the change in time, right? So the tangential acceleration would be the change in tangential velocity over the change in time, or that would be an average. So the instantaneous would be the derivative, the dv dt. Similarly, the angular velocity, the rate at which the angular velocity is changing, would be d omega dt. It's also related to this through the radius of the circle, so it would be at divided by r. And finally, the centripetal is the acceleration toward the center, and that's the tangential velocity squared over r, or omega squared times r. And the best example to illustrate this would be the one that we used in the problem. Now, if it's just a disk, there's nothing to focus on, so we'll use the flag. And as the flag goes around, it has an angular velocity, and if that's increasing or decreasing, then that's what we mean by the angular acceleration, the change in angular velocity. But as it goes around, the flag has a tangential velocity, and if it's speeding up, that tangential velocity is increasing, and that would be how we determine the tangential acceleration, the rate at which the tangential velocity is increasing. Now, additionally, we know something moving in a circle, even if it's at a constant speed, where there's no tangential acceleration, it's still bending. So if it's moving at a constant speed, it's bending toward the center at a constant rate. And that's what we mean by centripetal acceleration, the rate at which the direction of the velocity changes. And that is measured by these two equations from the equation sheet. So there are your equations, and there's a good example. Okay, that's it.